Let's wait for 2 3 minutes. So that I will start. Okay, let's start. So this is the ninth week problem solving sessions for the course regression analysis. Okay. So as we do every time, that the first thing which we will do is that we will solve the assignment questions for week 8. Next, we will go towards some practice question which will be useful for solving week 9 assignments. Practice question. But these practice questions are mostly based on the concepts of week 8 only, what we have discussed in the last problem solving session of the week 8 contents of the NPTEL, whatever it has been discussed. So based on that, those practice questions are there. So these particular week 8 contents are useful in solving the week 9 assignment questions. Along with that, of course, we will discuss uh, descriptively the week 9 contents. And of course, you will find some questions related to the week 9 contents as well. So these are the three broad things which we will be doing today. Okay, let me just switch off the camera. Yeah. So let us first start with the assignment questions. So week 8 assignment questions, we will start first. Okay. So let me go to the week 8 assignment. So it is asked that which one is not a measure of influential or potentially influential units. So there are several options. You can see that leverage is one of the options. Cook Weisberg is there, D beta, and Cook distance. So out of that, the if you look at the first option, that is leverage. So leverage is, we know that leverage point is that point where there is an unusual x coordinate. So this we have discussed already. So of course, this is one of the units of potential influential observation. So we cannot neglect this. Uh, the next is that BF beta. We have seen this BF beta, which is dependent on I and J, where I is the ith observation and J is the J regression coefficient. Okay, so it depends on these two, and this is one of the quantity to which we get the influential observation. That which of the observations is an influential observation. So this is also a valid influential observation unit. Okay. The next one is that what we have is Cook's distance, right? So Cook's distance is useful. Cook's distance is also useful to calculate leverage point, right? To identify leverage point. We have seen this. Okay. Since in the question it is being asked that which one is the influential point and potential influential. So potential influential is also a leverage point. So are these three are potential influential units. Okay, this identifies that this is the influential observation. However, there is an option called the Cook's Weisberg. This is actually a test. This is a test to understand or to identify the homoscedasticity. Okay, what is this? This is actually the meaning of this is that when variance of epsilon j is equal to sigma square, whether it is equal to sigma square or it is not equal to sigma square is what we are trying to identify through this. It will not tell you that which observation is the leverage observation or influential observation, right? So it will only tell whether if you suppose draw a residual plot or something, so like this EI and say YI hat, okay, and this is EI equal to 0, the spread, every time we have said that if it is spread uniformly along this EI equal to 0 line, then we say that it is the variance of epsilon is equal to sigma square, which is homoscedasticity. So this Cook-Swedenborg test identifies whether or identifies that it is a test for this homoscedasticity or heteroscedasticity. Heteroscedasticity means it will not follow this kind of a thing. Okay, it will be scattered more and more from the center line, that is vi equal to 0. So this is the thing. So it identifies the homoscedasticity. Right. So this is so in the first question we have seen that this the three options like leverage point, DF beta, or Hooke's distance. These we have seen that these are used to identify the observation, which is a leverage observation or an influential observation. Leverage, which is potential influential, right? So these three options are other influential units. However, Cook-Weisberg test is a test to identify the homoscedasticity, which is to identify whether variance of epsilon is equal to sigma square or not. Okay, so it is not going to tell us. It is not a unit. It will ultimately direct to us that yes, some influential observations must be there in the data, but it will not tell exactly that which is the influential observation. So that is the thing here. So that's why this is not a potential unit. Fine. So let's go ahead. Which one is not a measure of influential units? Is the Cook-Weisberg. So Cook-Weisberg test is also not there in the content. So you can just go through this, or you can go through further any other notes and things. Okay. Second question is that which statistics can help us detect the multicollinearity. So this is completely related to the multicollinearity content. So as you can see, all the things that you look at, of course, the variance inflation factor is one which talks about the multicollinearity out of all these things. So I'm just skipping it because we know. Okay, just I write here for the second question. It is the VIF. Okay, so it is the variance inflation factor. And the threshold is the VIF should be greater than equal to 10. If it is there, then there is a surety, sure multicollinearity is present. Okay, so these are the this we have seen in the multicollinearity content, the week lectures. Okay, next is the third one. Let's see. So the third one has is saying that see the scatter plot below. So this is a scatter plot which is given. You have to, it is being asked that which of the following is a high leverage point with respect to the regression. So this is the regression line which is being drawn between x and y, which is given in the scatter plot. So which one is a leverage point? Now, what is leverage point? As we know that leverage point is that point which has unusual x coordinate. So just look at it. If all of the observations are mostly uh, contained below 50, right, in x coordinate, most of the observations or all the observations mostly are less than 50 in the x coordinate. However, an observation at the extreme what you call as right. At the extreme right, if you see, at say some 90 or 80 odd or something, that is nothing but having an unusual x coordinate. You can clearly identify that, right? So that observation which has x coordinate about 80, which is greater than 50, only one is present. That is the leverage point. So if you just come here, so what is the leverage point? The definition. We will go by the definition here. So leverage observation leverage point is that point which has unusual x coordinate, right? Unusual x coordinate. So in the graph, you can see that clearly that if you have this kind of a graph, which is given, and this is a regression line, so most of your points are lying below 50. X is equal to 50. I will show the figure again. So we have to consider the x coordinate. Just remember this because it's a leverage point. So x below x is equal to 50, you will find most of the observation except one observation, which is I think somewhere here, which is at some 80 or something. So that observation will be a leverage point because it has an unusual x coordinate, right? Very different from all other points. So that's why this is a leverage point. So let's go to uh, this scatter plot. You can see that yes, this one, the extreme right one, is the leverage point. Okay, so his coordinate is near 80, 70. Fine. Let's go to the fourth question. What does a normal probability plot help you to test? Of course, the normality of the residuals, because if you just remember that your normal probability plot, what we have done that time. So this is, I think, corresponding to the say week 7 content or something. So what we have done there, we have plotted the residual, but these are the sorted residuals, just like this. And this is your PI, the probability. So what we have done here is that this PI, this probability, is actually I minus half divided by n, where n is the total number of observations and I is the ith observation. Okay. So I is the ith observation and n is the total number of observations. So this is your probability. This is how the probability is being calculated. And suppose E1, E2, so on up to En. These are the n residuals if you have. What you do is that you have to sort it based on the value. So the sorted is that the lowest is E1, next is E2, and so on up to En. Okay. When this and these PIs are plotted corresponding to that, you will get, if you get the points near this straight line, then you will see that this is an ideal case of normal distribution. That means your epsilon is actually following some kind of a normal distribution, okay, with some zero and some sigma square. Okay, so this is what the normal probability plot tells. So it talks about the normality of the residuals. These are residuals, right? So normality of residuals. So normal probability plot tells you about the normality of the residual. So we have seen that. So it's all based on the previous concepts. Let's go to the next question. Fifth one. The table below represents the studentized residual Ri and the diagonal elements Hii of the hat matrix, while fitting a linear regression model with beta naught plus beta 1x plus epsilon and has 10 observations. Okay, so is observation 5 an outlying observation in terms of its x value? So we have to see that. So we have seen it in the last lecture that, so this is the fifth question, right? So there are 10 observations given, okay, and your y is equal to beta naught plus beta 1x plus epsilon, which is given. Okay, so it's a simple linear regression model, and they say that you check whether this observation 5 is outlier with respect to x-axis. That means is it a leverage point or not? That is what will be asked. Okay, why? Because leverage means outline, outlying observation in terms of x value, right? So this is the thing. Now, leverage point checking. How to do that? So earlier, what we used to do is that we calculate the studentized residual, standardized residual, and see whether the standardized residual and studentized residual they have a larger difference or not, or HII is very large or not. But how much is that too large? So for that, in the last lecture, we have seen that there is a criteria called H bar, which is nothing but K by N. K is the number of unknown parameters in the regression model. So this is the number of regression coefficient. So this is the number of regression coefficient, and N is the total number of observations. This is how this H bar is calculated. So this will act as a threshold. Okay. So what is this H bar therefore in this case? K is how much? Beta naught and beta 1 are two unknown parameters. So it will be 2 divided by the number of observation is 10. So this will be zero point 0.2. And the criteria to see, to check whether it's a leverage point or not, is that your HII should be greater than 2 times H bar. So 2 times H bar is what? 2 into zero point 0.2, which is equal to zero point 0.4. So HII should be greater than zero point 0.4. This should be the uh, threshold or the critical criteria, critical value. If it crosses zero point 0.4, then it's okay. Then we will call that it is a leverage point. If it is not, then it is not. So let's go ahead for the observation 5 and check HII. So for the observation 5, look at the HII. It is 0.67. HII, right? So it is 0.67. So if it is 0.67, so for H5 means I is equal to 5. This is 0.67 as per the table given. So which is greater than zero point 0.4. Therefore, yes, it is a leverage point. Okay. So observation 5 is a leverage point. Right. So this is how you check the leverage point with identify the leverage point. Okay. So this is the fifth question we have seen. Okay. Now the sixth one is that consider the data in the problem 5, same data, and Cook distance di can be calculated without switching a new regression function each time the different observation is deleted. This is the definition of the Cook distance we have discussed in details in the last lecture. Di can be rewritten as this. Okay, and then they are asking that calculate your D7. Okay, let's go ahead. I will write this formula and let's see what is D7. Simple, it's a formula based question, that's all. So just go ahead with question number 6, where your Di is the Cook's distance, which is given as Ri square, which is studentized residual of the ith observation, divided by K, same number of regression coefficients, into HII divided by 1 minus HII. So this is your Cook distance formula, which is given in the question, right? So what we need to find out is D7, right? How much is the K? K is based on this one, okay? So how many K are there? Two, beta naught and beta 1. Two unknown parameters, beta naught and beta 1, right? Now, R7 is how much, which is given in the question. So, R7 is 1.92 given. You can see it in the table also given 1.92. And H of 7 that is HII, that is I is equal to 7, is nothing but 0.08. Therefore, D7 can be easily calculated from the above formula. It's just a formula based question. 1.92 whole square divided by 2 into HII is how much? 0.08 divided by 1 minus 0.08. That's all. So D7 will be how much therefore? This will be say 1.84 into zero point 0.08. So I have already squared it and divided by 2. So this becomes 1.84 divided by 0.92. This will give you 0.16. Okay, so for the sixth question, D7, Cook's distance for the seventh observation is 0.16. But as we know that if you really have to apply some concept in a particular data set, as we know, one value of D Cook's distance will not tell you anything. You have to compare with all other observations. So immediate next question, you will find such kind of a question. 7. See, consider the data in the problem 5 based on the Cook's distance. Which observation is expected to be an outlying observation? That is the thing, right? There are so many observations here. You can see there are 10 observations here. Now, which of them is a leverage point? That is what the important factor. That is where the Cook's distance comes into picture. Okay, so you have observation 7 in the option, observation 4, observation 5, and observation 1. Observation 7 we have already calculated. So with the same formula, let us do it for observation 4, 5, and 1. So let's do it. Okay, so in the seventh questions, we have to check which one is having higher Cook distance or which is the leverage point. So observation 7, we have seen already, we have calculated already. D7 is 0.16. So I'm not calculating it again. Next, observation 4. Let's do it for observation 4. D4 is equal to R4 square divided by 2, because 2 will not change because K is always 2 for all the cases, because it depends on the regression model. Y is equal to beta naught plus beta 1x plus epsilon. Two unknown parameters. Let me just write it properly. Parameters, that is K is equal to 2. That's why we are putting here 2. Okay, into H of 44. H44 is 0.25. So let me just write H of 44 is 0.25. So I'm just writing it 0.25 divided by 1 minus 0.25. Right? So what is R4? R4 is given to be minus 1.85. Its square, because R4 square is there, divided by 2 into 0.25 divided by 1 minus 0.25 is 0.75. How much you will get? So let me see. Yes, I have calculated. This total entire thing will come out to 0.57. Okay, it's a large value as compared to observation 7. So if you have these two observations, based on that, you can clearly say that out of this, observation 4 is much more larger, whose distance is much more larger, and hence you will have this observation 4 as the leverage point as compared to these two. Let's go ahead with observation 5 and observation 1. So observation 5, your H55 is 0.67 given from the table. Okay, and R5 is 0.16 from the table. So just you have to calculate D5. How will you do it? R5 square divided by K is equal to 2, same, it will not change. H55 divided by 1 minus H55. Right? So R5 square 0.16 square divided by 2. This is 0.67 and 1 minus 0.67. That's all. So 0.16 square, you just calculate it out and it will come out to be about 0.026. Okay. So it is very small. Okay. And last is observation 1. Let's do it. And let me just write the values. H11 is 0.05 given. R1 is 0.03. Very small values, as you can see. So just calculate. This becomes 0.03 square divided by 2. This will be 0.05 and this will be 1 minus 0.05. Right? So this gives you 2.36 into 10 to the power minus 5. Very small. Okay. So out of all this, you can clearly see that this D4 is much more larger. Okay. So D4 being the largest, of all, therefore the fourth observation is a leverage point. Okay. So let me go to the question. Yeah, observation 4 is the correct. And finally, the eighth question. Suppose we have data set consisting of n observations, and there are one regressor variable. Okay. In order to identify possible influential observation, the total number of DF fits to be computed. Okay. So what is DF fits? Just let me write the formula, and then you will be easily able to understand that what will be the number of DF fits value. Okay. Just a minute. Yes. So let's go to the 8th. So DF fit, right? So DF fits, we have discussed it in the last class. DF fit of I is yi minus y, accepting this ith observation, this all I have divided by root over ms residual of the ith, means excluding the ith observation, each I. So it depends on I, where I is the observation. Correct? This is the ith observation. Corresponding to ith observation, df fit. So then how many df fits you will calculate? If there are n observation, so if we have n observations, then number of df fits will be how much? N. Because it depends on what? Only the number of observations will be n. Correct? So therefore the correct option is n. But had it been df beta, let me just give a small thing. Suppose it is df beta. So df beta depends on both I and j, where I is observation, j is number of regression coefficient or unknown parameters. So in this case, they say that there is a one regressor. Okay, one regressor is present means there are two unknown parameters. So this 2 times n. So 2n will be the correct option for the df beta. But here it is df beta. So n. So with this, I think we can end this assignment of week 8. Now what we will do is that based on the contents of the week 8, particularly the linear uh, the linearity thing which we have done in the last class, that reducing it to a linear functions. So that we will continue and we'll do some questions based on that. Okay. So after this testing for leverage point and influential observation, we have seen that how to do the transformation to linearize the model. Okay. So based on that, some questions are there. We will do that, and after that, we will go towards the week 9 content. Fine. So let's end this part and okay. So let's do some practice questions, and after that we will go to the week 9 part. So this is the practice question. Okay. So let's start with this. Can the model y, suppose this is y, okay? So y is equal to delta naught x I1 delta 1 x I2 delta 2 be linearized? This is the question. Okay. So how will you solve it? Y is equal to delta naught x I1 delta 1 to the power delta 1 and x I2 to the power delta 2. And this will be linearized. So how to do that? To do this, see, delta naught, delta 1 and delta 2, these are constants. Okay. So how to linearize this? Can we do some transformation to linearize this? Yes, we can. Let's see. So what is the model which is given in the question? Y is equal to delta naught x I1. Just I is nothing but the number of observations. This ith observation delta 1 and x I2 delta 2. What we do is that take natural log on both sides. Okay. So just take this log 1 will be anything, whatever in multiplication it is there. Just write it first step by step. This is the so log y will remain log 1. Now log of a into b into c. This is a, this is b, this is c. But it will be log a plus log b plus log c. We know that. So it will be log delta naught plus log of x I1 to the power delta 1 plus log of x I2 to the power delta 2. Right? So it will be log y, which is log delta naught. Now power comes. So log of a to the power b is b log a, right? So it will be delta 1 log of x I1 plus delta 2 log x I2. See, this is a linear relation. So what you now have to regress is between some y dash, which is equal to log y, some x1 dash, which is equal to log x1, and some x2 dash, which is equal to log x2. That's all. So you now regress in MLR, multiple linear regression model, between x1 dash, x2 dash, and y. Now, if you y dash, sorry, y dash. Now, if you regress it, whatever your intercept you will get. So, with this model, whatever beta naught, say hat, beta one hat, you will get, and beta two hat will be there. Three things will be there, right? So, beta naught hat for this model will be nothing but log of delta naught. Beta one hat will be equal to your delta 1 and beta 2 hat is equal to delta 2. That's all. So this kind of a relationship y is equal to delta naught x to the power delta 1, x1 to the power delta 1 and x2 to the power delta 2 can be linearized. And how we can do it? This. Okay. So the answer is yes. By one go you can just write. So that's all. This is one of the things. Similar question. Let me just put here. This is This is a question from, I think that practice questions which are given in the week 8, not week 8, week 9. There you will do this. So this is in an enzyme kinetic, sorry, enzyme kinetic study. The velocity of reaction y, so it is related to some biological aspects, so you can understand, is expected to be related to concentration x. And how it is related? It is given as this. So y of I, for the ith observation, y is gamma naught xi divided by gamma 1 plus xi. So I represents the ith observation. Just be careful. Okay. So can this be linearized? That is the question. So we have seen it. We have seen this kind of a question earlier also, and we have seen it in the last lecture also. I have done a similar kind of stuff. So what we can do to linearize? Let's inverse it, right? Let us reciprocate both sides. So let's do it 1 by yi is equal to, or you can just leave I for the time being, just write 1 by y. I is known. So this will be what? Gamma 1 plus x divided by gamma naught x. Okay, if you want, you can keep I. If you don't want, just remove for the time being I. So this 1 by y will be therefore gamma 1 by gamma naught 1 by x. Can I write like this? Yes. Plus 1 upon gamma naught x divided by x. This can be cancelled out. So finally, if I write, it will be gamma 1 by gamma naught 1 by x plus 1 upon gamma naught. This is how we can write. And this is a clear linear relationship we can see if we write y dash is equal to some gamma 1 by gamma naught into x dash plus 1 by gamma naught. See, this is a clear linear relationship. When we can write y dash is equal to 1 upon y, x dash is equal to 1 upon x. And if you fit this, and if you get, so just it will be a simple linear regression model between x dash and y dash. So you will get two coefficients, beta naught hat, beta 1 hat. So beta naught hat will be what? Remember, beta naught hat is the intercept, 1 upon gamma. And beta 1 hat will be what? Gamma 1 by gamma naught. That's all. So this is how you will get the thing. So it can be linearized. It can be linearized. Okay. So this is another question. And Finally, let's go to some variance related questions. We have seen variance stability transformation. So that also we need to see. So it is based on the what we have derived in the last class. Let me go to the next page. So the question is that if variance of y is equal to sigma y square is proportional to. See, this proportional to things we have done in the last class. Suppose it is proportional to the expectation value of y. Means what? Variance is proportional to mu. That is the mean. So we have seen this kind of a thing, right? And which is which is the useful variance stabilizing transform, which is variance stabilizing transform. So following options are given that the transformation will be what? Y square? Is it root y? Is it log y? Or is it y inverse? So what will be the transformation in y? Okay. So we know. Okay. So we have seen this. So I will not derive it once again because it's a huge derivation from the Taylor series and all. So what we have seen is that we generally get if your variance is proportional to the ey to the power something like q or something like that. Huh? So it's a power, right? Ey that is means to the power something. If variance is like this, variance of what? Variance of y. If it is like this, then we can the transformation of in y can be written as this. So f of y is some proportional to y to the power 1 minus q by 2 when q is not equal to 2, and it is y to the power, oh sorry, log y when q is equal to 2. Okay, so this is what we get if variance of y is proportional to expectation value or mean of y to the power 3. Then we can get it like this. Here it has been asked that your sigma y square, the variance of y, is proportional to ey to the power 1 is proportional to this only. So q is 1. So if q is 1, which one will be used? We will be using this one, right? So a for y will be transformed to y to the power 1 minus 1 by 2, which is y to the power half, which is root y. Therefore, the correct transformation will be root y. Okay, so this is your answer. Fine. So these are all based on the last class questions. And one more I will do, and then we will go towards the week 9 content. This question, which I will be doing right now, is similar kind of questions. These are all based on the previous concepts which you have done. So it is not a very difficult thing. So you will find most of the questions in week 9 are based on like this, but different functions. Okay. So let's do it. Suppose the question is, suppose we want to fit a no intercept model. No intercept model. What? How it will look like? Y it will be equal to yi is beta xi plus epsilon r. Okay, so there is no intercept. Beta naught is not there. Okay, only one beta, which is a slope. So this is a no intercept model. Now we want to fit using weighted least square. Okay, so suppose it is given that sigma I square, which is nothing but variance of yi, which is not sigma I square. This is equal to a function c into xi, where c is some constant. Okay, so variance is given to be like this. So in this case, how will you find the least square estimator of beta? So how? to find least square estimator of beta. That is what you need to find out. Okay. So let me stop here. This I think will not be able to understand right now. Let us go to week 9 contents. Once we just introduce this weighted least square model, then we can clearly come to this question and solve it. Okay. So let me just keep some space here. Okay. So this will be enough, I think. This we will come. So you can see that here the weighted least square is being used. Okay. Because your sigma I square or variance of yi is not equal to sigma y square. That is what the important thing, because you will able to apply this what do you call as least square method only when epsilon is normal of 0 comma sigma square. So sigma square should be there. So variance of y or variance of epsilon, both are same. This has to be sigma square. But here it is not valid. So if it is not valid, we will not be using this particular way. Okay. So we have to use the weighted least square. So this we will do today. Weighted least square. So we'll come to this one. So let me just leave it right now and we will come to that. Okay. Let's go to the what you call as the with 9 content. There you will we will be introducing that. Just a minute. So the week 9 contents. So what we were right now doing is that we have seen the model adequacy checking and all those things. What we are actually doing is that suppose we have some given data. The first thing which we have seen by in the last 2 3 lectures is that how do we know how do we know that the basic assumptions on the basis of which the basic assumptions on the base of which we were doing those simple linear regression fit or multiple linear regression fit, all those assumptions are right or not. Do we know that? No, we don't know. We have just assumed it and did some questions in the earlier lectures. But this point comes in the last 3 lectures where we were doing that. How do we know that the basic assumptions? What are those basic assumptions? We have discussed in details, but let me write it again. Basic assumptions are correct or not. So all these techniques or things we are doing to understand this one. Okay. So what are the basic assumptions? Like E of epsilon I, the residual, is equal to 0 and variance of epsilon I should be equal to sigma square. If any of this is not valid, then our basic assumption is not valid. Then the simple linear regression, what we have derived, the fits which we have done, cannot be done in that way. Okay. So to understand whether this is correct or not, what we have done is that we have used model adequacy checking. Model inadequacy checking. Right? This process we have gone through, where we have seen that hat matrix, then student-sized residuals, and all those residual plots and all these things we have done. And to check this, we require residual plots. So one of the important plot is residual plot, which through which we can understand many things. For example, let me just repeat it once more. So this is your suppose one of the residual plots. How the residual plots are made? This is EI versus YI hat. Correct? And we have seen that there is a value, say EI equal to 0. If the scatters between this EI and YI hat are aligned like this, are between these two bands, we say that this variance of epsilon I is actually equal to sigma square, and this is a satisfactory model. However, if you go to a plot like this is YI hat, this is your EI, right? And this is your EI equal to 0 line. But now it is suppose an open funnel kind of a structure like this, like the scatter sunlight going farther away and away from this EI equal to 0 line, then in this kind of residual plot, we say that V of epsilon I is not equal to sigma square. It can be like this, it can be like this also. See, this is your EI, this is your YI hat, this is your EI equal to 0 line. It can be like this also. Anyway, so this is also the same thing. Unsatisfactory model, variance of epsilon I is not equal to sigma square. So basic assumptions are getting violated. Of course, there are other residual plots also where this same variance is violated, which is a double bow kind of a structure, and the nonlinearity presence. So this is your EI, this is your YI hat, EI, YI hat. So in the from the last two lectures, we are doing this only, right? So this is your EI equal to 0. This is also your EI equal to 0. In one case, it's a double bow structure where Y is in proportion between 0 and 1. We have seen it. And another is your curved band structure. This is the presence of nonlinearity. Okay. So in all the last four cases, we have found out that this variance of epsilon is not equal to sigma square. That means the basic assumption is getting violated. So in this case, we cannot use. So in these cases where variance of epsilon is not equal to sigma square, there we cannot use the direct linear regression method. We do generalized, generalized weighted least square technique. This is one of the methods to improve. Okay, weighted least square technique. Right. So this is your. So let me start with this particular thing. Let me write it first. So linear regression model, linear regression model with non-constant variance, which we have seen, like in the question which I have put, where c into xi square, we have seen that, or c into xi. So there, the variance is not constant. Okay, so non-constant variance can be fitted by method of weighted least square, which we will be doing. First we will see it in the theory, and then we will apply it in that particular what you call the question. So this is weighted least squares, right? So then let us just take a simple linear regression model, SLR. Okay. So in that we know that it is like this, right? Beta naught plus beta 1x plus epsilon. This is the general simple linear regression model. And S, the that is the SS, what you call it, SS, sum of the square of the residual is what? Is nothing but this I of course going from 1 to n. This will be yn minus beta naught hat, because your y hat is actually beta naught hat plus beta 1 hat. Epsilon will not be there here. So it will be beta 1 hat xi whole square. That's all. So this is your sum of square of residual. I is equal to 1 to n. Okay. Just remember, these are the just first class. Same thing. Okay. We are doing. Okay. Now, but for weighted residual, when variance is not constant, we use weighted residual. So now this weighted least square requires a weight W. So weighted least square. What we do is that instead of just simply writing like this, we just multiply it with some weight W1. Means each observation corresponding to that there will be some weight. How to calculate this weight? We will see. Entire week 9 content is based on that. So we will see that. But let us first write this. So for each of the observation, you can see Wi means for ith observation W is Wi, Yi minus beta naught hat minus beta 1 hat. Xi. Other things will not change. It will be same. So finally it will be Wi Ei square. Correct? So this is your sum of square of residual. Now what we do to calculate beta naught hat and beta 1 hat? Same thing we will do. So delta S by delta beta naught hat will be just write the summation. So it will be 2 Wi Yi minus beta naught hat minus beta 1 hat xi. And with a minus sign, of course, because you are differentiating with respect to beta naught hat. It is minus. So this should be equal to 0 because error has to be minimized. So based on that, we are getting one equation like this: Wi Yi minus summation Wi beta naught hat minus beta 1 hat Wi xi equal to 0. This beta naught hat you can keep outside the summation. That is fine. And finally, another equation will be delta S beta 1 hat. That should be also equal to 0. So what you can write? 2 Wi. This will be, see, this Wi is not differentiated with beta naught. These are constant values. Okay. So this will be then how much? Yi minus beta naught hat minus beta 1 hat xi into minus xi. Correct? Because we are differentiating now with respect to beta 1 hat. And based on this, we will get another equation as Wi Yi xi minus beta naught hat, which can be taken outside later, Wi xi minus beta 1 hat Wi xi square is equal to 0. So these are the two equations which we get. Solving these two equations, we will get beta naught hat and beta 1. So this is the concept of weighted least square technique. Okay. This is the concept of weighted least square technique. We will go further, but just remember that this is the concept of weighted least square technique. Now, if this is the concept of weighted least square technique, let us go back to this particular question and let us solve it. I think this is enough. We can easily solve it. So, one information is given here that your variance is not constant. It is c times xi. So, we have to use what? We have to use this weighted least square technique. Okay, one information is enough to tell you what you have to use. So this is telling you the same thing. Okay, so let's do how to solve. So question is that how to find the least square estimate beta. So least square estimate of beta means you have to calculate beta naught hat and you have to calculate beta 1. Okay, this is no relation. So slope is not there. Beta, this you have to calculate. Fine. So for the same thing, we write that S is equal to, so I is equal to 1 to n, that is fine. But you have what? This is yi minus beta hat xi. Correct? Because y hat is equal to beta hat xi. That's all. This is you have. This you are having. Based on that, you are writing like this. Right? It should be square into some weight. What is that weight? Okay. This weight, remember this weight Wi is actually divide 1 upon sigma I square. Why we are getting it? We will see today. This is why. This is based on the week 9 thing, which we will be doing today later. But for the time being, for solution or solving this particular question, just just take this that Wi is 1 upon sigma E square. So we will do this all these things. Okay. So 1 upon sigma E square. So what it will be? 1 upon C xi. Actually, this question should be put in the last, but I wanted to do it right now. Okay. So this is what the thing is. So weight is, always remember, the weight is 1 upon sigma square. So this is what we have done. Now you can just easily solve it. So just you have to do what? Delta S by delta beta hat and put it equal to 0. So if you do that, what you will get? So this is the summation 2 times yi minus beta hat xi divided by 1 upon cxi and into minus xi. Correct? Because you are differentiating with respect to beta hat. So this xi goes, what you get? Minus 2. You are getting minus 2 and you have yi minus beta hat xi. That should be equal to 0. Minus 3 you can remove. So this will be summation yi is equal to beta hat summation xi. So beta hat will be equal to summation yi divided by summation xi. So once you have figured out what is the weights and you know that it will be the weighted least square technique, then you can easily calculate based on the previous techniques. Okay. So this is your estimator. This is what you require. Okay. So, but question remains, why this Wi is 1 upon sigma E square? We have found out from the week 9 content only that if your sigma square or the variance is not equal to constant sigma square, if it is varying, then you have to use the weighted least square technique. That is what we have done. But in the weighted least square technique, I have only told you that there will be multiplication of Wi, weight. Now, what is this weight? I am telling you here that Wi is 1 upon sigma E square. Why? That is what we will be doing next. Okay, so this is a type of problem which will come in the assignment questions you will might have seen. So you can easily solve this right now. Okay, so now no questions left. We will just go through the theory and establish why or how this Wi is 1 upon sigma square. And number two is that if you given some data, not this kind of a question which I have given, some data are given, how do we calculate these weights? That's the thing. Okay. So these two things which we will be doing and we will be wrapping up today. Fine. So after we have done this weighted least square technique and found out these two equations, there is a theorem which is very important, which we call as the Gauss-Markov theorem. Okay, Gauss-Markov theorem. So there will be a statement of this theorem. So suppose you are using multiple linear regression model, y is equal to x beta plus epsilon. You should know that P of epsilon should be equal to 0 and variance of epsilon should be equal to sigma square into I. Okay. So the least square estimates are unbiased and have minimum variance when compared with other estimators that are linear combinations of y. So this is a statement which I'm just writing it from the lecture notes. Okay. So this is linear combinations. of Ys. Okay. So it just says that the best unbiased linear estimator beta hat, which we have already calculated, that is x dash x inverse x prime y. Right. But what will happen if this is not right? That is what we are dealing with. So this we have already calculated that b hat beta hat is this. And this is an unbiased estimator. We have also seen that. Okay. So Gauss-Markov theorem says that if this is a multiple linear regression model and this following assumptions are there, then the best estimator is this. Fine. This is known. All these things are known. What next is that we will apply it for where variance is not equal to sigma square. So those things we will be doing using weights and all those things we will be applying. For that, let me introduce an important thing, which is positive definite matrix. Positive definite matrix. It is important to understand whatever the property derivations and all those things. So positive definite matrix, suppose A is an n by n matrix, okay? Uh, Let us write say M. Okay? M is an n by n matrix. We call this a positive definite matrix if some z prime nz is greater than 0. What is this? So for all non-zero vector or vectors, whatever z, vector z in R to the power n. Okay, so one of the examples which are given, suppose the identity matrix M is equal to 1, 0, 0, 1. So you take Z8, Z naught square or Z naught and Z1, suppose. Okay, and suppose Z naught and Z1 are real and at least one of them is positive. If it is like this kind of a condition is there, then if you write Z dash MZ, this will give you Z naught square or Z1 square. And this will be always greater than equal to 0 or greater than 0. Okay, because one of them is both are real, first of all, and square of the real quantity will be a positive quantity. So it will be greater than 0. Okay, so then M will be a positive definite matrix. Okay, and there are many examples which are shown in the lecture of the week 9. You can refer to that positive definite matrix. But I just wanted to show some properties of positive definite matrix. Two properties I just wanted to write. First is positive definite matrix. Positive definite matrix is always a symmetric matrix. Remember, positive definite matrix is a symmetric matrix and all its eigenvalues, that is lambda, are positive. Just remember this. This is one of the properties of positive definite matrix. Second important property is that it is invertible. Invertible, that is inverse exists. Determinant of that matrix is non-zero. Okay, so these are the two important properties. We will be using these properties. So that's why I just, and why we are focusing on positive definite matrix? Just a minute. Okay, why we are considering the positive definite matrix is because every positive definite matrix, every positive definite matrix is a covariance matrix. Covariance matrix of some multivariate probability distribution. Okay, so all the covariance matrices are positive definite matrices generally. Okay, most of the covariance matrices are positive definite matrices. And why we are dealing with a covariance matrix? You will see that this whatever we write, suppose this variance of beta hat, there you say sigma square into some matrix, which is your covariance matrix, right? So that there it will be useful. It will come. Okay? So suppose you consider some model y is equal to x beta plus epsilon. It's a MLR, you can see multiple linear regression model with assumption that E of epsilon is zero, but variance of epsilon is some b times sigma square. It is not equal to sigma square, some b times sigma square. Okay, it cannot be written as sigma square into I. We are writing now generalized b square. This matrix B is positive definite. Okay, this is a positive definite matrix. Remember. Okay, now how when this kind of thing happens, it happens. This happens when this happens when observations Y have unequal variances or observations are correlated. Okay, when these two things occurs, there you will find that B of epsilon becomes B sigma square, which is a positive definite matrix. This B is a positive definite matrix. Sigma square is some constant, but B is positive definite. Okay, but in general, in case of in the ordinary least square method, B of epsilon should be equal to sigma square. That is the full stop, nothing else. But here, suppose you get some data set where you are finding the B of epsilon is B times sigma square, something times sigma square, where B is a positive definite matrix. Then you have to use this kind of a generalized least square techniques or weighted least square technique. Okay. So in this case, okay, in this case, your Gauss Markov will be violated. Gauss Markov theorem is violated because Markov theorem it starts with the fact of this, but here it is not identity matrix. Okay, okay. I can be a positive definite matrix, no doubt about that. But here this V will not be equal to I. That is the thing which is different. Okay, so you cannot write beta hat as x prime x inverse x prime y. This is not a best linear unbiased estimate. Okay, this sometimes the best linear unbiased estimator is called blue. Okay, so this is one of the point. Now then, how to do it? How to go out from this and find out a beta hat, which will be a best linear unbiased estimate. So for that, everything is there. So suppose your actual model, now to come out of this, to get the BLUE, what we do is that we have suppose actual model is suppose this y is equal to x beta plus epsilon. Okay, what we do is that we do some transformation. So we do some transformations. Okay, and hence the transform model becomes some g times y is equal to g times x times beta plus g times epsilon. So what we are doing is essentially is we are transforming by multiplying, pre-multiplying with g. Some g is some matrix. Okay, so this is the transform model. Some transformation requires to be done, otherwise it cannot be removed. We cannot find a best linear estimator. Okay, now if you do variance of gy, oh sorry, g epsilon, because epsilon is our main thing. So variance of g epsilon will be equal to sigma square g v g prime. Why we are writing like this? Just remember, if you have variance of say c times epsilon, c is a constant. How will you write? It will be c square variance of epsilon, correct? This c square is fine. Variance of epsilon we have seen. What is that? V into sigma square. So V into sigma square. Sigma square is some constant. Okay. So V sigma square you can find it here. And this C square in matrix can be written as G into G dash. So since this is based on some matrix multiplication, so it has to be written like this. Now, to get a best linear estimator model, which we have seen for the Gauss-Markov theorem, this part should be what? This part should be I, isn't it? Because if you just go ahead here, see, variance of epsilon should be equal to sigma square I, right? So this part, the extra part which we are getting when we have seen that V of epsilon is equal to V sigma square, the extra part we have to make some way. We have to, so some way we have to transform this GVG dash into I, identity. If it is there, then the transform model will be, means from this transform model, we can calculate some beta hat, which will be a best linear unbiased estimate. So that will be that is what our requirement is. Okay. So this is what the problem is. Okay. So let me just write that for best linear unbiased estimator of beta, okay, best linear unbiased estimator of beta can be obtained by ordinary least square method. Okay, so we have to some way we have to do this. So we have to choose G in such a way that your G V G prime becomes equal to I, and hence it will satisfy the Gauss-Markov theorem. That's the thing. So let's see what we can do. So what we require is G V G prime should be equal to I. Correct? So what we do now is that we post multiply with G prime inverse. So can I write like this? G prime inverse. Okay. So GV, this will be what? G prime into G prime inverse. This will be I. This will be G prime inverse. Okay. Now the GV becomes equal to G prime inverse. Okay. Now pre-multiply with G inverse. So it will be G inverse G V is equal to G inverse G prime inverse G prime into G inverse into G, which will be I, which is V, that is G inverse G prime inverse. This becomes V, which is G inverse G prime inverse. Okay. So this is your V. Great. This is fine. Now, if you do its inverse, V inverse, what it will be? G inverse G prime inverse, its whole inverse. A B inverse will be what? B inverse A inverse. So G prime inverse inverse G inverse inverse. Correct? Which we can write. Any matrix is inverse, again its inverse becomes the same matrix. So it will be G prime. So V inverse is equal to G prime G. Correct? So this is how it has come. Now come to beta hat. Okay, what we are talking about, this is beta hat for the transformed model. Remember, because we cannot use the actual model. Actual model has a problem because variance of epsilon is now V sigma square, not sigma square. Remember, that's why we have got for a transform model by multiplying with G, some matrix. With that, if you have to calculate beta, then what it will be? Simple. We have written that beta hat is what? Somewhere we have written, right? Uh, yeah, this one. Ordinary one. X prime x inverse x prime y. For the transform model, x is now what? Gx, y is now what? Gy. So just write that. Okay. So it will be now Gx prime Gx whole inverse Gx prime Gy. Can we write like this? This is for the transform model. Okay, because x has now been transformed to gx, y is now transformed to gy. So let me write x to gx, y to gy. For that, if you have to calculate beta hat, then you can write like this. Okay, so let's further write. Okay, gx transpose x transpose g transpose gx inverse g. So again, so it will be x transpose g y. G prime G is what? V inverse. We have seen it. So X prime V inverse X inverse X prime V inverse Y. This is your beta hat now, right? This is your beta hat. Now, if you have to calculate variance of beta hat, what it will be? It will be sigma square. Just remember the previous thing. We write here x prime x inverse ith element, right? But here we will write x prime v inverse x inverse its ith element, whatever, beta. Okay. Now, okay, so this we have already done. Now, it is always possible. It is always possible to find a symmetric matrix G by using orthogonal decomposition. What is orthogonal decomposition? I will write decomposition of some positive definite matrix. V. Okay, that's the thing. So how to do the orthogonal decomposition is like this. So V is equal to U prime lambda inverse. Okay, so since V is a positive definite matrix, it is a symmetric matrix, and therefore we can do this orthogonal decomposition like this. Okay, so this is based on the concept of linear algebra of orthogonal decomposition. Now V inverse, therefore, will be what? Just U inverse lambda U prime inverse. Okay, you can see it. Okay, what is this lambda? Lambda is diagonal matrix of eigenvalues. Okay, and U is matrix of eigenvectors. Okay, so this is how the decomposition is done. Fine. So now what we can write about G? See, V inverse is equal to G prime G. Correct? Now this V inverse is also U inverse lambda U prime inverse. Suppose we say that G is equal to lambda to the power half and U prime inverse. If I write like this, can it be valid that G prime G is actually equal to this? If you do it, it will be. Okay. So if you just write G prime, it will be lambda to the power half will be as it is. There will be no change in this. What it will be? U prime inverse prime. So U prime prime it will be U inverse. Okay. And finally, you have your what do you call as G. So G is what? Lambda half U prime inverse. Correct. So now, if you just write U prime G, which is V inverse, see it will be same. U inverse lambda half into lambda half and U prime inverse. So it will be U inverse lambda U prime inverse. That's all. So we can write. So just write lambda. So G is equal to lambda to the power half U prime inverse. Okay. So this is the thing. Now this is the concept of the generalized least square. Now weighted least square. So whatever we are doing here from this part, positive definite, this one. This is generalized least square technique, where we have seen that how to make a transformation using some G matrix and ultimately finding out what is G based on orthogonal decomposition. Okay, generalized least square. Okay, but weighted least square is one of the is a particular case. Okay, weighted least square is a case of generalized least square. Okay, now suppose your B of epsilon is like this: sigma 1 square, 0, so on up to 0, 0, sigma 2 square to 0, and so on. This will be sigma n square. Okay. Suppose this is equal to V. Okay. Now we know that V inverse is equal to G prime V. Okay. Can we choose therefore G is equal to V to the power minus half? Just look into it. G is this, G prime will be same, V minus half, so it will be V inverse. Okay. So this is a particular choice of V. So if I write G is this, then what will be your what will be your G matrix therefore? Just taking the reciprocal and root, correct? So it will be 1 upon sigma 1, so on up to 0, 1 upon sigma 2 up to 0. So all diagonal elements with 1 upon sigma. Okay. And then what will be your V inverse? V inverse will be just the square of this, correct? Isn't it? See, V to the power minus half is this. So V to the power minus 1 will be what? Just square of that. So this 0, 0, so on up to 0, 0, 1 upon sigma 2 square, 0 to 0, and so on. Go ahead. This will be 1 upon sigma n square. Okay. So this is your V inverse. And now look into that for the transform model beta hat. What we have found out? X prime V inverse X inverse X prime V inverse 1. Okay. This V inverse can be replaced with W. This is your way. Okay. So when we were doing simple linear model and simple linear regression model, we have found delta S by delta beta hat and all that using W, right? So if you do a multiple linear regression model, this W, these weights becomes actually V inverse. Okay. Therefore W therefore become equal to is proportional to 1 upon sigma I square. Okay. That's why we can write Wi sometimes equals to 1 upon sigma square. Okay, so this is the concept. Perfect. So from where this expression coming is? When we have seen a transform model, we have seen this kind of a best linear unbiased estimate. Okay, and actually, when you do weighted least square technique, this V inverse is actually your weights, and V inverse we have found out as 1 upon sigma square. That's why we can write like this. Okay, so this it will be more clear if you go through all the lecture notes. So this is very simplistically I have told. Okay. So now question is that how to calculate these weights. So in the last maybe 20-25 minutes, we will be understanding through a through an example, simple example, which is there in the videos also. You can look into it. I have taken a part of it and will explain how to calculate the weights. Okay. Yes. Okay. So next question is that now that we know that this wi is equal to 1 upon sigma I square, but how do we calculate, because sigma square is not every time known from the sample data, correct? Because you have to calculate some sample variance. Okay, but how to calculate this wi's? For that, what you do is that some steps has to be followed. So the basic question which I put here is that how to find the weights given some xy data. So this xy data does not mean that only one x will be there, one y will be there. There can be many. But let us take a simplistic case. Let us look for simple linear regression part. Then we can see. Okay. So suppose the first step is, suppose data is given as xy. Okay. So what you have to do is that you feed the model using ordinary least square. Okay. So consider again. So consider simple linear regression model. So y will be beta naught plus beta 1x plus epsilon, and its fit will be y hat will be beta naught hat plus beta 1 hat. You calculate residual y minus y hat. It will be in matrix form. I'm not writing I here, so okay. The immediate next thing is that you plot a residual plot, because residual plot will give you an idea that whether variance of epsilon is really equal to sigma square constant or it is not constant. If it is not constant, then you have to go for calculation of y. If it is constant, sigma square, go ahead with the ordinary discrete fit. That is absolutely fine. So suppose the data which I will be giving for that, suppose we are getting like this. Okay. Suppose we are getting, this is ei equal to 0, suppose this is ei, this is yi hat, all suppositions. Suppose this is like this, some open funnel kind of a structure. Then what you can conclude from this, since it is an open funnel structure, it is definitely sure that if p of epsilon I is not equal to sigma square. If it is not equal to sigma square, then what? Then we have to go to calculate the, we have to go towards a weighted least square technique. Okay. So From here, you just check whether constant variance, constant variance assumption is getting violated or not. Okay. If it is getting violated, then least square, the ordinary least square, fit is inappropriate. Okay. So what then? Then you have to go for need to go for weighted least square technique. Okay. So this is your checking tool. At first, you go ahead with your fit, plot a residual plot, calculate residuals, plot a residual plot, see whether it is giving an open funnel structure or something else. If it is giving a nice banded structure and all the data are centrally equally spaced, then variance of epsilon is constant. That is fine. Ordinary least square is valid. Beta hat you can calculate. That will be the best unbiased least square estimate. But if this kind of things happens or something else happens, where variance is of epsilon is not a constant, not equal to sigma square, then you have to go for the weighted least square technique, where we know that weights are equal to 1 upon sigma square, but there is a way of calculating it. Okay. So this is now the data which I will show. This is say some maybe some 15 observations I have taken. So the data below which I will write is 1 to 15 observation from the week 9 lecture which is there. Week 9, I think some video two or some lecture you figure it out. I think the last part. Okay. So I have taken it from that. Okay. So just I write it and you see. So this is y, this is x. Okay. I just write it clearly. So this is 81464 72661 72344 9074398588 96507. This is just to demonstrate that how we calculate the weights. 574 114133, then 115814 123 181 131 434 40 564 151 352 146 926 and 13096. 15 observations are there. Corresponding X value also I will write. So it is 3000 3150 3085 5225 5350 609 8925 9015 8885 8980 sorry 8950. Okay. 50 9000, then 11, 345, 12 to 75, 1 to 400, and 1 to 525. So what we do now is that we make a cluster of almost similar values. Okay. So, but clusters has to be seen it from the x values, not from the y values, because x are independent. Y is dependent value. So don't create clusters on the dependent value. Clusters always has to be done in the independent coordinate. So x is the independent coordinate. Remember, x I have written in the right hand side now. Okay, so this is one of the clusters of 3000. This might be another cluster. See, there is a huge difference between 5350 and 6090. So we cannot use 6090, let it be like this. Another cluster is this. Okay, and the last cluster for this 15 observation is this. Okay, of course, there are many observations which are present after that. I have not written it here. Okay, so these are clusters corresponding to this. These are the three clusters. Okay, these two and these up to this maybe, yeah, and up to this. After that also there will be many clusters and all. Okay, so what is next done is that we calculate x bar and sy square. Okay, xy square is the sample variance. Okay, and finally we calculate the w's. So x bar is averaging these three, the clusters. Okay, so it will be x1 bar, which is about 3078.3. This is x2 bar, which is 5287.4. Just mean of these three observations, two observations. This is x3 bar, which is 8955. And this is x4 bar. This is 1237.5. Okay, sy square. So based on sy, so it is the sample variance of these three observations. So that comes out to be 2679420. Okay, based on these three observations. Next, based on these two, you calculate sample variance 307,22010. How to calculate sample variance? You know this. Okay, so this is how the sample variance is to be calculated. Fine. And next is 52803698. So large values you can see. And 77280166. Okay. So this is how the sample variance is calculated. What we do is next is that we can clearly see as x bar increases, your sy square also increases. What we do now, so as x bar increases, sy square also increases. So it kind of fits a linear relationship. Okay, so a linear relationship can be established. Okay, a linear relationship can be established. So what we do for that, we fit simple linear regression model between x bar and sy hat square, because now it will be a fitting. Okay, so based on all the observations, not only these observations of x up to x4, there will be many after that. So you can refer to that example. So they have found out that this sy hat square will be minus 7376216 plus 7819.77 into x bar. Okay. Now, to calculate weights, what we do now is that we replace we replace x bar as x, right, and calculate sy hat square. Okay. So, and then what we do is that we calculate Wi, which is actually 1 upon sigma I. We have seen sigma I square. We will write instead of sigma I square, because sigma I square is many times unknown because we have only sample. So we write S hat Y I square. This is how the weights will be calculated. So I will show you. Okay, I will show you how the weights are calculated. Suppose based on this equation, we have got that this is the linear relationship. Okay, so let's look at for the first observation. Is so calculation of weight. Okay, first observation. So what it will be? So it will be minus 7376,216 plus 7819.77, right, into, so x bar will be replaced with x1. So what is x1? Just if you look it, this is the first observation, x1, correct? So this is 3000, right? So can we just write 3000 here? Yes. So if you write it, so minus 7376,216 plus 7819.77 into 3000. If you do it, your S51 hat square will come out to be 16083094. This is not the weight. This is the sample variance corresponding to the first observation. Correct? But the weight is what? W1 will be 1 upon S11 square. So this will be 1 upon 16083094. This comes out to be 6.217 into 10 to the power minus 8. This is your W1. If you look at the example, you will get the same thing as the W1. 6.217 into 10 to the power minus 8. Okay. Similarly, for the second 3150, just I calculate this one. So SY2 hat square for the second observation, you will have 10 minus 7376216 plus 7819.77 into 3150, because we are replacing x bar with xi. Here, two, second observation. This gives you 17256,059.5, and hence W2, which will be 1 upon 17256,059.5, and this comes out to be 5.795 into 10 to the power minus 8. So the second weight is this. Okay, so here you can write this. So this is the way from the data the weights are calculated. Okay, this is the very large long procedure through which the weights are calculated, and then you can fit weighted least square. That's all. The matrix problems and all. Fine. So once we calculate the weights, the next procedure is what? So this is how weights are calculated. So once these weights are calculated using weighted least square technique, least square make a fit between x and y. So you will get, means for this particular case, the above example, for above example, remember there is only 15 observations here. There are many observations there. So just this is corresponding to all. Okay, 975.56 plus 7.922 into this is what you will get. Once you get this fit, you again check the residual plot, but there is a difference here. Check the residual plot. Remember, for the weighted least square technique, your EI square now will be WI into EI square. Remember, this is not EI square, this is residual. Okay, so this is WI EI square. Remember this. Okay, Why what I'm writing? Just let me go over there where I have just started. Yes, see. Okay. The weighted least square. S is nothing but Wi ei square. Therefore, when you are plotting the residual now, you cannot plot ei versus ei versus yi hat, but you have to plot ei times wi to the power half a versus wi hat. This is now you have to plot. This is the zero value of that. Check whether it has come like this or not. It is coming like this or not. If it is coming like this, then you are clear that the transform variance of epsilon is actually equal to sigma square. Hence, everything is now fine. So, whatever the linear relationships you have got, that model is fine. Okay, so this is the last point, last part of the uh, weighted least square technique. Okay, just remember this. And yes, for multiple linear regression model, you can. So this I make a point. This is whatever I have shown, this example from the Week9 content. This is for simple linear regression. For multiple linear regression, you write this beta hat. We have seen x prime weight x inverse x prime weight into y. Okay, you have x matrix, you will have y matrix. We know how to calculate. Only thing is that the w will be multiplied by. That's all. Okay, so this is how the uh, best unbiased linear estimator can be calculated. Okay, and for relationships like what we have seen in the practice questions, that suppose variance is given as cx square. For there, if you have to see the weights, it will be w will be 1 upon sigma square. That you have to clarify, and we have seen that how it can comes. Okay, so with this, I think I will end today. So many concepts, weighted least squares particularly, and the questions which I have solved, those will be important in solving, and the contents will be helpful for solving the questions of week 9. Okay. Apart from this, if you have any questions, you can ask, or otherwise, I will just recap it once more, just quickly, and then we can leave. So, any questions on this part? Okay, so if there's no questions, then just I will quickly go through what we have done today. So apart from solving, yeah, tell me. Hello? Yeah. Hmm. Yes, yes, yes. It will be calculated based on this cluster. You have formed a cluster, right? These three values. So based on these three observations and this formula, S y hat square, the sample variance, what you calculate. From there, you have to calculate like this. Okay, and then you have to fit between this x bar and sy square, linear fit. Huh? Yeah. So you will have these kinds of points, like you have these points. Suppose now your x will be now x1 bar, x2 bar, x3 bar, x4 bar, and so on. There will be many other observations, and corresponding sy square also you calculate. So it will be sy1, suppose sy2, suppose, and so on. Okay. And based on that, you fit a graph. So this will be sy hat square or sy square, whatever you want it to write. So this is your x bar. Based on that, you will get a fit. This is a fitted line. This fitted line is written here. Now what I'm doing is that this x bar, we are replacing it with each and individual observation, not the cluster. We are replacing it with 3000, 3150, and then calculating the sy square corresponding to that. Okay, this we are calculating. Now that 1 divided by that becomes my width. That is the thing. Okay. So, so this is, so is it now clear or require further? Okay, fine. So, most importantly, I would just go through this part. So these are the linear relationships. You have seen it. It's clear, I think. Only important part is this, where you can see that sigma I becomes equal to C into xi, not constant quantity, but constant times some xi. Here you have to see weight is equal to 1 upon sigma I square. The entire derivation we have done to understand this, why it is 1 by sigma I square. And now if you know that W is equal to 1 upon sigma I square, we have just put it in the weighted least square method. That is just the residual square times the weight. And weight is 1 upon sigma I square. So that is what we have done. Based on that, you can calculate beta hat, whatever you require, you do. Okay. And for multiple linear regression, the beta hat for this kind of case becomes, or weighted least square case becomes like this. Uh, where I have written in the absolute end. This one. X prime W X inverse X prime W1. But W again is 1 upon sigma square, but it will be in a different way. So we have seen that when you have given data, you have to take a cluster. So 3 or 2, whatever you want. So based on that, you calculate X bar of those clusters and sample variance of these clusters. So one values will come and you will just fit it. You will just fit it between X bar and XY square, right? And based on the fit, you get a fitted model like this. Now, X bar, this X bar has to be replaced with each observations, like 3000, not the cluster, 3000, 3150. And based on that, you calculate the fitted SY square. Now, once you get the fitted SY square, then everything is done. You can calculate the weights as I have shown. Okay. So I think we can stop here. Okay, I think I can stop here. Network issue is there, but I will post the lecture notes and uh, the recordings also. Okay, thank you.